So continuing with the state changes, sublimation. Sublimation is a transition from a solid directly to a gas without going through a liquid. The opposite of sublimation is deposition, going from a gas directly to a solid. So here we have an illustration of an ice cube. We've got water molecules here, and you notice there's a pattern. They're all lined up and orderly, because that's what ice does. These particles are not still. They are not moving relative to each other, but they're vibrating. And the amount of kinetic energy that they have depends on the temperature. The temperature gives us an average kinetic energy, but some have high kinetic energies and some have lower kinetic energies. So if you have a molecule at the surface with high kinetic energy, it may have enough kinetic energy to break off into the gas state. And that's known as sublimation. Now, it doesn't happen very quickly, but it does happen. So that would lead to a vapor pressure. And so solids also have vapor pressure. It's a very low vapor pressure generally, but they do have vapor pressures. Sublimation is what carbon dioxide does. Here we have a chunk of dry ice. It's called dry ice because it doesn't melt. Regular ice in your cooler melts and gets your sandwiches all soggy, right? It's wet ice. This is dry ice. It never melts. It doesn't make a liquid. It sublimes. It goes directly into the gas state. Now, this is a substance that at room temperature, you've got it's not really room temperature because that's really, really cold. But this is going to have a very significant vapor pressure, right? Because it is actively subliming. Sublimation occurs in your freezer. If you leave ice cubes in the back of the freezer, or maybe they get caught up in the ice cube maker and get left there for a long time, and you finally dig them out, they're a lot smaller than the fresh ice cubes. And that's because they've been subliming. So the water molecules that were part of the original ice cubes have gotten into the gas state and moved somewhere else in the freezer.
So it's not necessarily, I always thought it was the air blowing over the ice, like taking it.
No, it's actually subliming. And you've probably observed this phenomenon too, ice crystals inside an airtight bag of frozen food. This happens a lot with like French fries and tater tots, right? You buy a bag of tater tots at the store because you were hungry and everything sounds good, and then you just kind of never get around to cooking them until you've like run out of food, and then you're like, ooh, this is okay, I'll get these out, and it's like months later. You open the bag and you dump them out on the pan, and there's the tater tots, and what else? A whole bunch of ice crystals. Why do they pack all those ice crystals in with the tater tots? Don't they know that it's difficult then because you have to get rid of it, otherwise they're going to melt and get your tater tots all soggy? Well, they didn't put those in there. The water in those ice crystals was originally in the tater tots. It's sublimed out of the tater tots. It's now a gas inside this airtight bag. Can't really go anywhere. So eventually it's going to condense somewhere else and freeze. And the crystals will grow. Sometimes they're really pretty. They'll grow, and they'll just keep doing that. So that's dehydrating your tater tots. They're not going to be as good. Foods in the freezer, we call it freezer burn, but it has nothing to do with burning. They get dehydrated. Meats do it too. You leave a piece of meat in the freezer and it's not well wrapped, and a couple months later it's nasty, right? Because all of the water has left from the outside of it. So you can prevent that a couple of ways. You can use a deep freeze, which is colder than a regular freezer, because the colder the temperature, the slower the sublimation. Or you can seal the food without any airspace. So you could use a vacuum sealer, or you could wrap the food very tightly in aluminum foil before putting it in a plastic bag, and that will reduce the amount of airspace around it. Because in order to sublime, the water molecule has to go into the air, right? If there's no air to go into, it might sublime, but then it's probably just going to come right back, right? So you can cut down on freezer burn by wrapping your food better. Any questions? Yeah.
Can we stop to vaporize that?
Can you stop the vaporization of the dry ice? If you put it in a really cold environment, you can.
How about the pressure?
I think increasing the pressure.
Increasing pressure raises the boil.
It really depends on it depends on its. Some things when you put, like ice, if you put pressure on it, it melts. A lot of things, if you put pressure on them, they'll freeze.
One time I put in the glass and then
Oh, yeah. Yeah, so if you put dry ice in a sealed container, the CO2 gas will build up and it will break. It definitely will break. And people like to joke around or talk about making a bomb with a 2-liter soda bottle. It's a really, really bad idea. Very bad idea. And I think there's criminal prosecution that can happen if you do stuff like that.
There's
So
a
tell.
generator.
Hmm?
I don't know if it's on Clovis or what, the generator got fired.
Yeah.
It's not-
When I'll tell you the story. I didn't tell my other students, but when my husband was a little boy, his mom worked in a pharmacy, and they received lots of shipments of medicines that were packed in dry ice to keep them cold. They also sold pickles in those giant glass jars. So one day he had a little too much time on his hands. I think he was like 8, 10 years old, something like that. Very dangerous age. Put some dry ice in the pickle jar and sealed the lid in the backyard. And as he watched it, he realized that maybe this was not a good thing. And he realized that this was going to end badly. So he got his BB gun and he laid down on the far side of the yard, as far away he could get in the yard. He laid down flat and he shot the pickle jar with his BB gun. It made a really loud noise. His uncle came running. There were not glass shards everywhere, though. It exploded so thoroughly that the glass was in such small pieces it was basically sand. The lid came flying down, but there was nothing else left.
Wow.
And Uncle Joe comes in and he sees what's happened and he says, "Stupid kids," and he goes home. True story. But putting carbon dioxide into a sealed container could cause significant bodily harm. So I'm officially telling you, never ever do that. And that's not one of those wink wink things. No, really, don't do it. It's a very, very bad idea. Now, if you want to use it to pop a stopper out of a bottle or something, that's fine. But you don't want that pressure to build up. Any other questions? Fusion. So fusion is a fancy word for melting. And I used to have a hard time remembering that fusion and melting meant the same thing. So what helps me is to think about chocolate chips. Which, thinking about chocolate chips helps a lot of things, right? If you heat chocolate chips, they melt and they fuse together, right, into one big lump. So melting and fusion, the same thing. So if we take that block of ice with the vibrating molecules and we increase its temperature, the particles are going to vibrate more and more. At some point, they're going to have enough thermal energy that they can partially overcome the intermolecular forces that are holding them together, and they can slide around. And the solid will become a liquid. So here we have another heating curve. Here we're starting at -10, and we're adding heat, and we're increasing the temperature of the ice. When we get to the melting point, freezing point is just which direction you're coming at it from. At the melting point, additional heat that's added just causes faster melting. The temperature will not rise until all the ice has melted. And that's true with any solid. There's a flat place in the heating curve when you have a state change. Because as you're adding heat, all of that heat is going into is going into breaking or partially breaking those intermolecular forces. Once it's all melted, then the temperature rises again. I think this is one of the reasons that 0 degrees Celsius was chosen as standard temperature, because it's very easy to achieve. If you have a container with water and ice, you can be quite certain that it's very close to 0 degrees Celsius. You don't even need a thermometer. And so if you need to do an experiment at 0 degrees Celsius, all you have to do is put your thing in an ice water bath, and you've got it.
So that's why, is that why when you put drinks into ice water, they cool quicker than they do if it's just ice?
Well, that's a little different. So if you put a can of soda in a bucket of ice, and you put another one in a bucket of ice water, right? The one that's in the ice water will cool faster. But that's because you've got better contact and better transfer of heat. The air doesn't transfer the heat very well, but the water does a much better job. And if you really want your soda or your beer cold, throw some salt in there, and you can actually get it even colder.
That's how you use that to make ice cream.
Yeah, and we'll talk a lot more about that, and we'll actually make ice cream. So melting is an endothermic process. We understand that. How do you get ice to melt? You put heat into it, right? Well, how much heat do you need? Well, heat of fusion. Delta H FUS. Heat of fusion is the heat required to melt 1 mole of the solid. So we can write a chemical equation, H2OS to H2OL, and that the heat for that reaction will be the heat of fusion. So it's positive 6.02 kilojoules per mole. Freezing is an exothermic process, which is not as intuitive, because you don't think of ice freezing giving off energy, but it does. The way you get ice to freeze is you suck heat out of it. The same amount of heat is released when a mole of water freezes. So it's November, it's getting a little chilly. Where I live in Reedley, there are a lot of citrus trees, and it's been getting cold, and so they need to keep the trees from freezing, and specifically to keep the fruit from freezing, because if the oranges freeze, cell walls break and your crop is lost, and then that's devastating to the economy, and it's just blah 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 blah, big mess. So one of the things they do is they water the field. They flood the field with water. Then as the temperature drops, gets down to 0 degrees Celsius, the water begins to freeze. But the temperature where that water is freezing will not drop below 0 degrees Celsius until all the water has frozen. And so it's releasing energy, keeping the temperature at 0 degrees. Oranges don't freeze at 0 degrees. I remember the numbers in Fahrenheit. So 32 is the freezing point of water in Fahrenheit. So the oranges are in danger around 26, 27 degrees. If it stays down there for a few hours, it's really bad news. So we use the freezing of water to keep the field warm. And then they have these big blowers, like giant windmills, but they don't make energy from wind. They use energy to make wind, and they blow the air around, because you need that warmer air down where the water's freezing to get up where the trees are. Any questions? It's chemistry, keeping your citrus safe. If we compare heats of fusion with heats of vaporization, heat of fusion is generally a lot less than a heat of vaporization. And there's a graph here. In the blue is the heat of fusion, in the bright pink is the heat of vaporization. We'll see it takes a lot more energy to vaporize a mole of water than it does to melt a mole of water. Because in vaporizing something, turning it into a gas, you have to completely break all the intermolecular forces. Whereas to melt something, you only need to partially overcome those intermolecular forces. They can still be attracted to each other, they're still touchingly close, but they just need to be able to slide around to be a liquid. These are not the sorts of numbers that you memorize. There's no need for that. If you need heats of fusion, they'll be provided to you.